Welcome back to the deep dive. Our job, really, is simple. Take these complex tech ecosystems and, well, make them make sense quickly. Actionable intelligence. That's the goal. Today, we're cutting right to the core of the Nutanix Database Service, NDB. We've pulled together a bunch of technical sources, mainly looking at the foundational stuff you'd need for the Nutanix certification on NDB, version 6.10 specifically. But look, our mission isn't about passing a test. It's about using that focus material as a map. We want to skip the long manuals and just pull out the essential operational bits, the architecture knowledge you need to really get how NDB manages databases. Think of this as your fast track to understanding NDB.
Yeah, and that focus material is super useful. It forces you to concentrate on what actually matters day to day. We're talking core ideas, stuff a pro needs to know under pressure, the architecture, security, how automation works for the lifecycle. These are the things that really define what NDB can do.
Okay, let's start right at the bottom layer. Provisioning databases is messy, right? Different OSs, specific binaries, lots of fiddly OS-level interaction needed. If NDB is the brain sending out orders, what's the actual hands-on worker, the component doing the work on the VM?
Right, that critical piece, that's the NDB agent. It's really the operational backbone here. And you need to remember, this is agent-based for a good reason. The NDB agent has to be installed on every single database server VM that NDB is going to manage. If it's not there, NDB can talk to the hypervisor, sure, but it can't get inside the guest VM to manage the database itself or the OS.
Ah, okay, that's a key distinction. So the agent isn't just passive, it's actively doing things inside the VM.
Exactly. It's responsible for executing, well, pretty much every database lifecycle operation. When you click provision or clone or patch in the NDB console, the control plane sends that command down to the agent. The agent then does the actual work-changing file paths, updating binaries, creating service accounts, all that OS-level stuff. It's a translator between the high-level request and the on-the-ground reality.
Okay, let's make that practical. Say you're modernizing, right? You've got an existing database server VM already running fine in Prism Central. You want to bring it into NDB, get that automated time machine goodness, automated patching. Before you can even click register in NDB, what's the absolute must-do step?
Yeah, the non-negotiable prerequisite is getting that NDB agent installed and running on the existing database server VM first. If the agent isn't there and running, NDB just can't establish that communication channel it needs. It won't know the server state, can't manage it, simple as that. The agent is the key.
Got it, agent first. So once we have management sorted, the next big headache is often standardization, right? In a big environment, you can't be manually sizing every new database VM. Tweaking vCPU, memory, disk, it's chaos. Leads to drift, performance issues. What does NDB have to stop that? To define a reusable sort of hardware blueprint.
That's exactly the job of the compute profile. Think of it like standardized t-shirt sizes for your database VMs. Small, medium, large, whatever you define. The compute profile nails down the virtual hardware config, the vCPU count, the memory allocation, the VM disk capacity. Every database server VM you provision using that profile gets exactly those specs.
And the benefit there isn't just saving a few clicks during setup, I assume.
Oh, much bigger than that. It's about operational consistency, predictable scaling. You use a profile, every dev database, for instance, gets exactly 8 vCPUs and 64 gigs of RAM every single time. It just eliminates performance variations from manual sizing errors, and it makes capacity planning way easier because you're deploying known units.
Okay, compute profile locks down the VM specs. Makes sense. Now, where does the actual database data live? We need to talk storage abstraction.
Precisely. We're moving from the VM definition to the data itself. When NDB provisions a database, it needs to sort of hide the underlying storage details from the database. Right. And it needs to manage the mount point so the data persists. That role. That belongs to the volume group. So the volume group, that's what the database interacts with for its storage, like its view of the disks. Essentially, yes. It manages how the underlying storage resources are presented to the database server VM. It handles mounting the volumes. The important thing is it abstracts away all that underlying complexity. The DDA works with the database. The volume group just makes sure the storage is there, reliably mounted. Quick tip. If you're ever troubleshooting a provisioning failure, and the database setup looks okay, but the storage volumes aren't showing up inside the VM, check the volume group configuration. That's often the link.
Right, good tip. Okay, this is where things get really cool, I think. The automation, specifically data synchronization with Time Machine. Picture this. Dev team needs a fresh copy of the production database every morning. Like clockwork, 9:00 a.m. They don't want to manually clone it daily. How does NDB automate that?
NDB handles that really elegantly using its Time Machine feature. Instead of scheduling a data refresh on the clone, See, the clone itself was originally made from a time machine snapshot of production. So instead of doing a whole new clone operation every day, you just tell NDB, hey, for this clone, automatically grab the latest available snapshot from the production time machine every day at 9:0 a.m. It just keeps rolling forward, synchronizing the dev environment with production data. Zero manual work for the admin after setup.
That covers getting the fresh data. But wait, we just pulled production data into dev. That sets off alarm bells, right? Sensitive data, PII maybe? The data has to be masked. The database credentials need changing so dev can't accidentally hit production. Can NDB build that security step right into the workflow?
Yes, absolutely. That's a key strength of the cloning workflow. It allows for integrated post-clone operations. And the two really critical ones you mentioned are running a custom data masking script, vital for compliance, and automatically changing the database credentials.
And why is having those in the workflow so important?
It makes security the default. By baking the masking and credential change right into the cloning process, you eliminate that risky window. You avoid having sensitive data exposed, even briefly, in a non-prod environment, and you prevent production credentials from ever existing on a dev machine. It enforces that separation right from the moment of creation.
Okay, makes sense. So that's daily refresh. Let's think longer term. Compliance. The main time machine snapshots, they probably keep data for, what, weeks, maybe months? But auditors' regulations, they might need years of retention, maybe stored off-site. What's the NDB feature for that kind of long-haul off-site data retention?
For that extended retention, you need to configure a long-term retention policy, or LTR. The LTR policy is built specifically for archiving database snapshots way beyond the normal operational window of the primary time machine. Typically, this archived data gets moved to a secondary storage target, often cheaper storage, maybe off-site, ensuring you meet those multi-year compliance and audit needs without filling up your primary cluster.
Got it. LTR for the long haul. Okay, that covers the data lifecycle pretty well. Let's pivot to high availability, segment 3. Keeping the database running even during maintenance. Let's say an admin needs to do a live volume migration, move a running database VM and its storage to another Nutanix cluster. Key requirements: zero downtime, zero data loss. What underlying platform feature has to be set up on both Nutanix clusters involved?
For that level of synchronous, zero downtime, zero data loss migration, you absolutely need a specific Nutanix platform feature enabled between those clusters. That's Metro availability.
Metro availability. Why specifically Metro? Why wouldn't a standard disaster recovery setup work for zero downtime?
Because standard DR is usually asynchronous. There's always a small lag, right? A recovery point objective, RPO, greater than 0, you might lose a few seconds, maybe minutes of data. Metro availability, though, sets up synchronous storage mirroring between two clusters, even if they're miles apart, usually within a certain latency boundary. NDB can only pull off that zero downtime live volume migration because Metro guarantees the data is written to both sides simultaneously. It makes the two clusters act like one single, highly available storage fabric for that VM.
Right, synchronous is the key for zero data loss there. Okay, heavy stuff. Let's secure something simpler. Communication, alerts. NDB spots a problem, needs to email the admin. It connects to an SMTP server. To make sure those emails aren't sent in the clear, what encryption options does NDB support for that SMTP connection?
Pretty standard stuff here, thankfully.
Ah.
The two supported encryption options for securing that SMTP connection are SSL and TLS. You know, sometimes people use the terms interchangeably, especially SSL, but NDB supports these established protocols to make sure alert emails, which might contain operational details, are sent securely.
Good standard security hygiene. Okay, final segment. Who gets to do what? Access control. In a big company, the DBA team, well, they shouldn't be able to accidentally reboot the whole Nutanix cluster, right? But they do need to provision, clone, patch, manage databases every day. What's the minimum NDB role someone needs to actually provision a new database instance?
The minimum required role for that specific job provisioning a new database is the database admin.
And why that role? What's the difference? What can a database admin do? And maybe more importantly, what can't they do compared to, say, a super admin?
That distinction is crucial for separation of duties. The database admin role is tailored for users who manage the database lifecycle itself. They can provision, clone, patch, refresh, manage database parameters, basically everything within the NDB service related to databases. But crucially, they cannot touch the underlying Nutanix infrastructure settings. They can't configure Prism Central, they can't mess with storage containers directly, network settings, or things like Metro availability status. It keeps the DBAs focused and efficient on database tasks without giving them keys to the whole infrastructure kingdom, which could affect platform stability.
That separation makes a lot of sense for security and stability in large orgs.
So here's a question for you, the listener, to think about. If NDB standardizes the hardware footprint and the cloning process so effectively, how does that fundamentally change the old, painful challenge of troubleshooting performance inconsistencies across potentially hundreds of databases? And maybe more interestingly, what new automation opportunities does that level of standardization unlock? Think infrastructure as code, integration with cloud management platforms. Where could that lead?
That standardization really does feel like the key to the next level of efficiency. Well, thank you for walking us through this deep dive, really getting into the operational heart of NDB.
My pleasure. Always good to break down the architecture.
We really hope this helps you connect the dots, and we encourage you to keep exploring how these Nutanix components fit together to tame the complexity of database management. We'll see you on the next deep dive.